So let us start again. Okay, so we did SGD with a full analysis for this. So that's what we are trying to do, is a pure theoretical kind of a course where we try to prove things, mostly optimization for machine learning. And here we are done with SGD, mini SGD with various conditions like PL conditions, strongly convex, Lipschitz continuous, and so on. And SGD as such is used, but and still used quite a lot. But one of the variant of SGD, which is called SGD with momentum plus. Now this is usually more popular. Okay, so and then there are variations of this like RMS prop and Adam and so on. So it's a good idea to also have some knowledge of how SGD plus momentum behaves, and in particular, does momentum really help us in a better way compared to SGD. So today we will focus on momentum, momentum based methods like SGD with momentum. So first of all, let us define what are momentum based methods. Okay, so I will define something called stochastic momentum. So stochastic momentum, and the way it is defined, or I can kind of like write an algorithm. So this is from the notes, so it's algorithm 7.1, and the usual assumptions still hold. So let assumptions sum of Lmax smooth hold, and let the initial solution x naught be a d-dimensional vector, and let m at the initial value of the m, let us say it's 0, and let eta, I mean the gamma t, be a subset of this. So basically gamma t lies between 0 and infinity. Be a sequence of step sizes then, and let beta t be a subset of 0, 1. So beta t is another parameter we want it to be in the interval 0, 1. Be a sequence of momentum parameters then the momentum algorithm is written as mt is equal to beta t m t minus 1 plus grad I t, I mean grad of, let us say, f I t x t. So this is how the momentum I mean the momentum term is defined, and then now we will make an update for the xt minus gamma t m t. So as you can see, compared to the SGD method, which looked like this, and in the momentum place you had the gradient, but now what you do is you are doing some kind of an average of your gradient. So this is like your previous gradient, okay, and then the current gradient, and you are doing some kind of a weighted sum of the gradients, and that's called momentum term, and that helps sometimes because of the randomness involved in the methods. Sometimes going in average helps a lot, okay, with descent type methods. So momentum can bring stability in your method, or make it less oscillatory. So if I'm doing like this while converging, then the fact that I'm taking average of the two successive gradients, then this gradient points in this direction, this gradient point in this direction, then if I have to kind of like take the average, then average will kind of start going in this direction, okay. So I mean, let me draw it like this. Okay, a lot of oscillations is happening, and then if I have to take an average, then take a vector average, then I will shift this guy here. Okay, so basically, and then I will add it. See, if I added, the vector additions go in this direction. Okay, so basically, this is my let us say gradient number 1 and gradient number 2. So let us say gradient gradient at x1, let us say, and this is gradient at x2, the second iterate. Then the momentum based method says that, and so actually you were here, but then vectors I am allowed to kind of translate. So momentum based method says that take the average so that the oscillatory behavior can be minimized. So in general, I want to move in this m direction, which is MT. So this I call it MT. So I will descend in the MT direction, which will be the average. And this average will keep growing, as you can see, because it's a recursive formula. So if I am at a later stage, let us say, so this will be average of all this, okay. So not necessarily the successive one. So you will take all this average, and then maybe you will have an MT that goes eventually in this direction. So you are taking a history of those all the gradient computations that you did, and you are doing weighted average, and this weights can change also while at iteration t it can change at each time, but overall the idea is to go along some average direction, which usually helps in a stochastic gradient type methods. So this is the basic idea of momentum based methods, and this is what we are trying to understand. So so when doing an analysis of this, like let's say I want to prove the results that momentum based methods are convergent, then there are variations of these methods which are more useful than this one, okay, while doing some proofs. So so one of the way we can write this is something called heavy ball method, okay, heavy ball format. So if I have to write this in the heavy ball format, then the same iteration can be written as follows. So a remark on this is that if we use a momentum based method, then momentum algorithm, so I will put a remark, momentum algorithm has a complexity of order of 1 over epsilon square, and this is an improvement over SGD. this is an improvement over SGD for which we know complexity about only about the average of the iterates. Okay, so if you recall SGD, then for SGD we had complexity results for average of the iterates, and we were looking into X bar type, if you recall. But if we have a momentum, then last iterate convergence would be also possible. Okay, so this is the momentum based method that is frequently used in machine learning to train deep neural networks. These algorithms, compared to many other optimization algorithms that you see, there are so many sophisticated algorithms, and at the end of the day we study a lot more this because of the deep learning thing, because these guys are so much useful. So they look simple, and a lot of focus is going on in these algorithms. So as I said, we have seen SGD with batches, we have done concrete proofs, and we are looking at momentum based method. So this is our basic idea of momentum based method. Now it has advantages in the sense that I can prove last iterate convergence rather than proving the average iterate convergence. And to have that proof today, I want to see this in two different variants, same iterates but in two different variants. So the first one is called heavy ball format. So ways of writing momentum. So basically we will look into two ways. Another one is iterated averaging. Heavy ball method is all are equivalent basically. Okay, so heavy ball. So those who work on theory, machine learning, and also on, okay, they keep thinking about these variants. So in the heavy ball method, what we say is that this iteration can be written, this momentum, this two-step method can be written as follows, where the iterate updates are like xt plus 1 is xt minus gamma t hat, and then gradient of fit xt plus beta hat t xt minus xt minus 1. So can we see that, right? So what we are saying is that these two steps are same as this step, okay, where beta hat t that we have defined there is in 0 1. So beta hat t is in 0 1, and obviously it, the notations that we have, I believe, also used before when defining the stochastic gradient, is sampled uniformly. So it is the random sample that we are picking from n, and on that random sample we are computing gradient. Right now we are not considering the batch format, we are considering the batch size to be 1 basically. So we are just taking one sample, computing gradient at a time. So what it says is that the heavy ball method is equivalent to this. Okay, so in fact this can be this can be shown, and that's lemma 7.2 that says that the heavy ball method and the momentum method, they are same. So we can formally write this. So lemma 7.2, and it says that the momentum and heavy ball method are equivalent. So this is, let us say this is equation number. So I use the equation number same as the note so that you can also verify later on. And let us say this is equation number 59. So to make it precise, so more precisely, if xt is the iterate generated by let us say the momentum based method. So by momentum by 58, let us say, is generated by 58 with parameters. So in 58 the parameters are beta t and gamma t. So from with parameters then it also then it's similar to 59 with slightly different choices of gamma t and beta t. Okay, so then it verifies 59 with gamma hat is equal to gamma t. So gamma hat doesn't change, gamma hat is gamma t, and beta t is given by beta hat t is given by gamma t beta t by gamma t minus 1. So I hope you can see this, and with gamma minus 1 is 0, gamma the initial gamma is set to be 0. So is it true, right? So lemma says that both are essentially same, 58 and 59 are same. It's just that the choice of gamma, you have to rescale the gamma and beta. Okay, so basically what might be done here is, this is our iterate and we want to write down 59. So in 59 we only see x terms and gamma and beta obviously. So it seems like we have to substitute mt here and then rearrange the gamma and beta terms and see if with this gamma hat and beta hat we get 59. Okay, so this is what we are supposed to do. We are supposed to kind of get rid of mt somehow and get an expression only in xt, beta, gamma and gradient. Okay, so let us try to do this. So then let us start from the momentum, right? So starting with momentum. So momentum update was xt plus 1 is xt minus gamma t mt, and we will substitute the mt from there from 58. Because we are starting from the momentum, then we will use whatever steps are there in the momentum. So in this case mt is beta t mt minus 1 and the gradient term here. Okay, so it gets multiplied with gamma t as well. So minus, so this is equal to xt minus gamma t beta t m t minus 1 minus gamma t grad f I x t. You can write it as FIT here. So I have just substituted MT by this. I hope it's correct. So MT is beta MT minus 1 and the gamma FIT XT. That's right. Okay. So this is our, and obviously we are still seeing MT minus 1 there, which we want to get rid of. Okay, so we need to get rid of that MT also. So what happens at time t minus 1? At time okay, gamma t minus 1 also I can see there. So at time t minus 1, the proposal is the following. At time t minus 1, we have mt minus 1 equals to xt minus 1 minus xt by gamma t minus 1. So why is that, right? So let's see, is it correct? At t minus 1, xt plus 1 minus xt, I mean that's correct exactly. This is the second equation, right? So this is from the second equation, right? So from the second equation of 58. Okay, so from the second equation we are able to get rid of the mt minus 1. And so let us substitute this mt minus 1 above. So this, let us say this is some star. So now star becomes then we have xt plus 1 is equal to xt minus gamma t beta t, and then we are supposed to substitute mt minus 1, which is xt minus 1 minus xt by gamma t minus 1, and then remaining terms is minus gamma t grad FIT xt. Okay, so now we are supposed to rearrange and see whether it looks like 59. Okay, with this rearrangements that was proposed in the lemma. So let's see. So gamma t does not need to be changed. It seems to be, because gamma t, this is the term goes with the gamma t. Okay, so this I can take gamma hat t to be the same gamma t, and this term is fine. Now we have to see this term. So in this term we see that that beta hat t must be equal to gamma t bt by gamma t minus 1. So gamma t bt by gamma t minus 1, that's exactly what we have. So with this proper setting we have this for these choices of gamma hat t and beta hat t, we exactly have 59. Okay, so we can set gamma t to be gamma hat t to be gamma t and beta hat t to be the one gamma t beta t by gamma t beta t by gamma t minus 1. Okay, so with this choice we have the lemma 7.2. So what we say is that momentum based method can also be seen as a so-called heavy ball method, and there is a second equivalence which is called iterative averaging. So we will show an equivalence to that as well. Yeah, so I think we need only momentum for that. So I think this is better, and this we may not need. So the other one is something called iterative moving average. So lemma 7.3, and this is the algorithm, the momentum algorithm. Is equivalent to the following algorithm, to the so-called iterate moving average. Or sometimes called IMA. And this says that start from z minus 1 equals to 0. It's basically the initial z is said to be 0, and then iterate the z with z t minus 1 minus eta t grad fi t xt, and xt plus 1 is lambda t plus 1 t plus 1 plus 1 xt plus 1 by lambda t plus 1 plus 1 zt. So now what we are seeing is that the momentum method and then the heavy ball method that we saw, and then this is the third variant, they are all the same. But the reason why we are having different variants is that sometimes these are useful in the proof compared to the other one. So we will prove today that momentum based methods are convergent and so on. So but before we do that, let us try to show that this is equivalent to momentum based method. Okay. So in this case also, the parameters that these guys have needs to be adjusted. So we can say that more precisely, if xt is generated by momentum algo from parameters gamma t and beta t, then it verifies IMA by choosing parameters eta t and gamma t as follows, where we have beta t gamma t plus 1 is gamma t minus 1 gamma t divided by gamma t minus beta t, and then eta t is 1 plus gamma t, it is 1 plus lambda t plus 1 and gamma t, and then zt minus 1 is equal to xt plus lambda t and xt minus 1. Okay. So this is the iterate moving average, and we will show that this and this are the same. So let us start with the momentum itself. So we start from here and we show that it produces these kind of iterates. So if I start from here, these things are given to us. Okay, so at least what I know from the last one is that z and x are given in that form. So I will start from that. I will start from this. So what I know from here is zt minus 1 is xt plus So jet t minus 1 is xt plus lambda t and xt minus 1. Okay, so this is jet t minus 1, right? If we do it for jet t, meaning we increase the t by 1, then this is same as saying that this is jet t is x t plus 1 plus lambda t plus 1 x t plus 1 minus x t. So we increase the t by 1, and from there, if I look for take common for xt and xt plus 1, yeah. So it is gamma t minus 1 times gamma t divided to gamma t minus beta t. So what is?
The numerator and denominator both have gamma.
Okay. Oh, okay. Yes, I see. So okay. So first one is lambda t, right? This is lambda t. Okay. Thanks. So 1 plus lambda t plus 1 gamma t and xt plus lambda. Okay, everything is fine. Okay, and if we divide by 1 plus lambda t plus 1, we get actually the second equation of this IMA. Okay, so that's the way we could simplify this is taking the things common here. So 1 plus lambda t plus 1 and x t plus 1 and minus lambda t plus 1 x t. Okay. And if we divide throughout by 1 plus lambda t plus 1, we get the second equation here. Okay. And we are supposed to arrive here. And what we are given are these things. Okay, we started with we want to start with the momentum based method. So next is we will invoke this okay, actually we will use 7.2, so which was the heavy ball method. So because we know that momentum is also equivalent to that, so we will use lemma 7.2 using lemma 7.2, which is the heavy ball format. And in that case, the iterates were given by xt plus 1 is xt minus gamma t grad fit, and then xt plus beta hat t xt minus 1, and where the beta hat was given to be gamma t beta t divided by gamma t minus 1. So let us use heavy ball iterate. So this gives us how the xt are updated, and I believe we will substitute this. So that's what we are going to do. So we in the jet t, because we are looking to find this, and with a proper choice of these, I mean with the okay, so 1 second. So there is eta t here, Right, okay, I was looking for this guy. So with the eta t to be given like this, okay, so we are supposed to reproduce this. This is already kind of found out right now because that's exactly the zt. So from here, these things were given to us. So from here we found out how z and x are related, and dividing by 1 plus lambda t plus 1 exactly gives us this form. We can solve for xt plus 1. So this is kind of there. Now we want to get this. So hence we invoked lemma 7.2, and now in the z iterate we will substitute xt plus 1 by this and do some algebra and see what happens. Okay, so let us do it here. So if we substitute that z there, so then xt plus 1 becomes, I mean, we are starting with the zt. So zt is, 1 plus lambda t plus 1 x t plus 1 minus lambda t plus 1 xt. So I just copied over and then 1 plus lambda t plus 1, and then here I put this xt plus 1 from there. So this is xt minus gamma t f and so on. Okay, so I have it here, so I will just copy it from here. Gamma t grad f I t xt plus beta hat t xt minus xt minus 1 and bracket close, and then minus lambda t plus 1 xt. So that was the last term there. So we have this zt. So now it's about kind of rearranging stuff. Now in the claim we are supposed to reproduce or produce this zt minus 1, because we want to see this. The gradient is there. So what needs to be brought is zt minus 1 there, and we will look into that last term that was given to us, which is these guys that relates z and x. Okay, so what can we do here? In the last term I see xt, okay, and then the difference also I see, which is here. Xt minus 1 is there, this term, and this term I see. So xt plus, and of course we don't have the lambda t here, this is in terms of beta, and I have xt minus 1. Okay, so that can help in bringing the zt minus 1. Okay, that's then we have to force these lambda t to be in a way that it matches that the beta hat. Okay, so I hope you have a little bit of a plan what I'm thinking. So let us go with this plan. Let us bring out these two guys, because these two guys are the candidates that can give me zt minus 1 that I'm looking for. So I will do this one more step here, where I have xt, and then I also bring this term here. So plus 1 plus lambda t plus 1, and then beta hat t xt minus 1. Okay, so I have brought these guys, and the remaining term I see is minus 1 plus lambda t plus 1, and then gamma t grad of f I t x t and then the final term is minus lambda t plus 1 x t, which is also interesting. It seems like that seems to get cancelled with this. Okay, so I will write it first and then maybe cancel that. So if I see this term and this term, so they are negative of and they get cancelled, it seems. Okay, so I can write like this. So it seems that here I am left with xt. Okay, so it seems that here I am left with xt plus this term Okay, so what do we have? So the question is, can we bring jet t minus 1? Of course, if I have to bring that, then these guys have to be lambda t. Okay, so does this conditions follow given that b hat is there on the third one, gamma t beta t by gamma t minus 1, and does everything get in place, right, so that I get a gamma t. So what I can do is I can substitute the beta hat first. That will be the first step. So if I substitute beta hat plus first, then eta t goes with grad, right? So eta t goes with grad. Let us see also at the eta t. Oh, eta t seems to be fixed. Okay, it seems like we have the eta t in place, because if you see here, this term is eta t, and that's exactly what is given to us. Eta t is 1 plus lambda t plus 1, and then so this is exactly what eta t was supposed to be. So this term is already done. Okay, so what we are now looking for is that the remaining terms, will they give us jet t minus 1? And it should ideally, if we have not made any mistake, then so basically we have to figure out this constant. So let us try to kind of figure this out. So I will just focus on this term now, because in fact what I am looking for is that this term is exactly equal to lambda t. Okay, if I am done, then I can replace whole thing by jet t minus 1. So basically our focus goes directly into looking into this term. So is this equal to lambda t? Okay, so that's a proposition, right? So is this the thing, right? So if we can show with all the things we are given, then we are done. Okay, so let's see. Your first step could be you substitute the beta hat first. So if you substitute beta hat, then you have 1 plus lambda t plus 1 gamma t beta t by gamma t plus 1 right. So this calculation needs to be done. So let us do it here. So we can just skip the last one. So the beta hat is there, and what we are looking for is 1 plus lambda t plus 1 and we have beta hat t. So this is 1 plus lambda t plus 1. Beta hat is gamma t beta t by gamma t minus 1. Okay, so gamma t, where is this? Hmm? So it comes from the first? True? I mean, you have verified or? Okay. So if I solve for gamma t and substitute it there. So you see what I'm, okay, I see. So what you're saying is, if I solve for gamma t, then, so the proposal is that if I solve for gamma t from there, then whatever expression comes here, it will be of this form 1 plus lambda t plus 1 and beta hat t given by that. And what we are doing is the other way actually. We are going from here and we are seeing, we want to see whether gamma t could be found that way. In other words, what we are seeing is that these terms are 1 basically, because we are supposed to produce, no, not that, not 1. I thought gamma t was lambda t, but that's other thing, right? Yeah. So does it work the other way also? Are you sure about the other way, like solving for lambda t is
Yeah, but
does give you this?
it does, but there is one problem.
Hmm.
Gamma t plus 1 is there. It should have been lambda t plus 1 there.
Oh, okay, let me check then. Maybe. Yeah, that is correct. Okay. So by this we also found an error. So yes, that may be the reason why we were a little bit stuck, because with this it seems like some terms are visible now, because from there we see beta t, lambda t plus 1. I also see gamma t also I see there, and divided by lambda thing, all this seems to be working well now. Okay, so that was the error on our part. So I think the easiest way to do this is, yeah, I mean the way I thought maybe we can do that. So let us say this is gamma t beta t by gamma t minus 1 plus lambda t plus 1 gamma t beta t by, there may be easier way, I don't know, I may be doing it in a little bit silly way, but let's see. So gamma beta t, lambda t plus 1 gamma t divided by, okay, yeah, it does looks a bit, and I think a better, okay, this should be simple, but I'm just kind of saying, look, when you look for the easiest way, then sometimes you have. So what I'm looking for, okay, let me kind of get this 1 plus lambda. So I will start this beta t lambda t plus 1, and I will bring in plus beta t, and this is equal to gamma t minus 1 gamma t, and then divided by, or I mean lambda t and divided by gamma t. So this is lambda t and divided by gamma t. So I hope I have not done any mistake. So beta t, lambda t plus 1 plus beta t, and this is gamma t minus 1 gamma t divided by lambda t divided by gamma t. So from here I have 1 plus, so beta t 1 plus lambda t plus 1, and this is gamma t minus 1 gamma t, lambda t by gamma t. Okay, so we are supposed to produce lambda t, right? Okay, it seems to be coming now. So with this, I will substitute this guy there. So here I am looking at 1 plus lambda t. So basically this I will substitute. So 1 plus lambda t plus 1 beta t is when substituted by lambda t minus 1 gets cancelled from the top, and gamma And here let us write this. So this is gamma. I hope this was gamma, right? Gamma t minus 1, and then this is substituted by gamma t minus 1 lambda t by gamma t. Okay, everything gets cancelled, and this is indeed lambda t. This is a simple algebra, but yeah, one has to go through this. So indeed, what we find is that we come back to the iterate. So zt is equal to, now this becomes our zt minus 1. This is what we have shown with this guy is lambda, this guy is yeah, exactly. So just to recall, we had to produce this eta t is already produced, so this we already got hold of, and what we were trying to show is that there is a zt minus 1 here. So to get zt minus 1 here, zt minus 1 has the form like this. So then xt was already there, and xt minus 1 is already there. So only thing we have to say that the constant that we have before the xt minus 1, which is this guy here, this we had to show that it's lambda t, and that's what we have done. We have shown that it's lambda t. So now it's xt plus lambda t, xt minus 1. So this guy, now we can say that it is z t minus 1. Okay. So now the iterate is okay. Zt is zt minus 1 minus eta t grad fi t xt. That's what we were supposed to prove. Okay. So momentum method is equivalent to iterate moving average method. You can always like fix the constants by these relationships, okay, but at the end of the day you have these iterates, which is same as momentum based iterates.